Mole as a fundamental unit like meter, liter, second, etc. is equally important. It is indispensable for chemists and also highly valuable for biologists as well. A poor understanding and difficulty in realization of mole concept can lead to enormous errors and wastage of resources in performing scientific experiments. Due to erroneous calculations, experiments like biochemical assays, animal cell culture, polymerase, chain reactions, spectrometry and routine buffer preparation, and most of the analytical techniques require very good understanding of mole concept. This high-value note brings you a highly organized set of information of mole concepts, recent updates in the definition, and various problem-solving approaches in mole concept and concentration terms. The development of mole concept and definition of one mole has taken several decades. In relative context, we can imagine that the formulation of fundamental laws was the founding step, which was succeeded by development of some definition of mole. The term and unit mole had been in use in chemistry roughly the start of the 20th century. The atomic composition of chemical compounds can be described in a variety of ways, including molecular formulas and percent composition. The percent composition of a compound is calculated with a molecular formula. Divide the mass of each element found in one mole of the compound by the total molar mass of the compound. The percent composition of a compound can be measured experimentally, and these values can be used to determine the empirical formula of a compound. The atomic composition of a chemical compound can be described using a variety of notations, including molecular, empirical, and structural formulas. Another convenient way to describe atomic composition is to examine the percent composition of a compound by mass. Percent composition by mass. Percent composition is calculated from a molecular formula by dividing the mass of a single element in one mole of a compound by the mass of one mole of the entire compound. This value is presented as a percentage. Percentage composition of a compound is a ratio of one amount of each element to the total amount of individuals element in a compound, which is then multiplied with 100. The percentage composition of any given compound is nothing but the ratio of the amount of each element present in the compound to the total amount of individual element present in the compound multiplied by 100. Here we measure the quantity in terms of grams of the elements present in the solution. The percent composition of any compound is an expression of its composition in terms of all the element present. The significance of this composition calculation is found in the chemical analysis. We use the concept of mass percentage composition to denote the concentration of an element into a compound or a component in a mixture. We use this term to signify the total percent by mass of each element that is presented to a compound. It is important to note that we can calculate the mass percentage composition by dividing the mass of component by the total mass of the mixture. This ratio is limited to be multiplied by 100. Chemists often need to know what elements are present in a compound and what is percentage. The percent composition, the percent weight and mass of each element in a compound. Geothermal energy is heat within the earth. The word geothermal comes from Greek word geo and therm. Geothermal energy is a renewable energy source because heat is continuously produced inside the earth. People use geothermal heat for bathing, to heat buildings, and to generate electricity. Geothermal energy, form of energy conversion in which heat energy from within Earth is captured and harnessed for cooking, bathing, space heating, electrical power generation, and other uses. Heat from Earth's interior generates surface phenomena such as lava flows, geysers, fumaroles, hot springs, and mud pots. The heat is produced mainly by the radioactive decays of potassium, thorium, and uranium in Earth's crust and mantle, and also by friction generated along the margins of continental plates. The subsequent annual low-grade heat flow from the surface averages between 50 and 700 kilowatts per square meter worldwide. In contrast, incoming solar radiance striking Earth's surface provides 342 watts per square meter. Annually, geothermal heat energy can be recovered and exploited for human use and is available everywhere Earth's surface. The estimated energy that can be recovered and utilized of the surface is 4.5 times 106 exajoules, or about 1.4 times 106 terawatt-years, which equates to roughly 3 times the world's unknown consumption of all types of energy. The amount of usable energy from geothermal sources varies with depth and extradition methods. The increase in temperature of rocks and other materials underground varies 20 to 30 degrees Celsius and 30 to 54 Fahrenheit per kilometer, zero point 0.6 mile. Depth worldwide in the upper part of the lithosphere, and this rate of increase is much higher than in most of Earth's known geothermal areas. Normally, heat extraction requires a fluid or stream to bring the enemy to the surface. Locating and discovering geothermal sources can be challenging. This is especially true for the high temperature resources needed for generating electricity. Such resources are typically limited to parts of the world characterized by recent volcanic activity or located along place boundaries or within crustal hotspots. Even though there are a continuous source of heat within Earth, the extraction rate of the heat fluids and steam can exceed the reference rate, and thus use of the resource must be managed sustainably. Geothermal energy use can be divided into three categories: direct use applications, geothermal heat pumps, and electric power generation. Probably the most widely used set of applications involve the direct use of heated water from the ground without any need of special equipment. All direct use applications make use of long-term geothermal resources which range between 50 and 150 Fahrenheit. Such low-infrared geothermal water and steam have been used to warm single buildings as well as whole districts where numerous buildings are heated from one central supply source. In addition, many swimming pools, bathing facilities at spa, greenhouses, and aquaculture ponds around the world have been heated with geothermal resources. Other direct use of geothermal energy includes cooking, industrial applications, milk pasteurization, and layer scale melting. For many of those activities, hot water is often used directly in the heating system, or it may be used in conjunction with the heat exchanger, which transfers heat when there are problems, mineral and gas injection. Geothermal heat pumps take advantage of the relatively stable moderate temperature conditions that occur within the first 300 meters of the surface to heat buildings in the winter and cool them in the summer. In that part of the lithosphere, rocks and groundwater occur at temperatures between 5 and 30 degrees Celsius. At shallowest depth where most GHPs are found, such as within 6 meters of Earth's surface, the temperature of the ground maintains a near constant temperature of 10 to 16 degrees Celsius. Consequently, the heat can be used to help warm buildings during the colder months of the year when the temperature falls below to the ground. Similarly, during the warmer months of the year, warmth can be drawn from a building circulated around where it loses much of its heat and is returned. Depending upon the temperature and the fluids, low geothermal energy can be used to generate electricity. Geothermal power plants can produce electricity in three ways, despite their difference in design. All their controlled behavior of steam and used to drive electrical generators given the excess water vapor at the end of each process is condensed and returned to the ground, where it is treated for later use. Geothermal power is considered a form of renewable energy. A volcano is a vent chimney which transfers molten rock from depths to the Earth's surface through eruptions. Magma erupting from a volcano is called lava. Lava builds up around the vent and forms a cone. A volcano is currently active with erupting lava, releasing gas and generating seismic activity. An active volcano is labeled dormant if it is not erupted for a long time but could erupt again in the future. When a volcano has been dormant for more than 10,000 years, it is considered extinct. Volcanoes can remain inactive or dormant for hundreds of thousands of years before erupting again. During this time, they can become covered by vegetation, making them difficult to identify. How explosive volcano eruption is depends on how easily magma can flow or trap gas. If magma is able to trap a large amount of gas, it can produce an explosive eruption. Volcanoes can have many different appearances. Some volcanoes are perfect cone shapes, while others are deep depressions filled with water. The shape of volcano provides clues to the type of size of eruption that occurred. Eruption types of size depend on what magma is made up of. Three common volcano forms are shield volcanoes. Shield volcanoes of broad, flattened, dome-like shape created by layers of hot and runny lava flowing over its surface and cooling. When magma is very hot and runny, gases can escape easily. Eruption of this type of magma are gentle, with large amount of magma reaching the surface through vast lava flows. Because the lava flow easily, it can move down gradually so or degrade distance from the volcano when the lava flows are low enough for humans to outrun or walk them. This type of magma reaches temperatures between 800 degrees Celsius and 1200 degrees Celsius and is called basaltic magma. Examples of shield volcanoes in Asia Pacific region include the Uyuni volcano in Fiji, Duneji volcano in New Zealand, and Tweed volcano in Australia. Composite volcano, also known as stratovolcanoes, composite volcanoes are formed from explosive eruption. This eruption creates steep side cones when magma is slightly cooler, its viscous, thick, and sticky, which makes it harder to get bubbles to expand and escape. The magma of these eruptions has higher silica content than the magma that forms shield volcanoes. When there is high concentration of silica in lava, the silica molecules link together by sharing oxygen atoms. These bonds are very strong and make the liquid magma act more like a solid. Examples of composite volcanoes in the Asia-Pacific region, including Mayon and the Pinatubo volcanoes in the Philippines, Tambora, Merapi, and Sinabung volcanoes in Indonesia, and Mount Rufai and Mount Takanaki in New Zealand. Caldera volcano. These volcanoes erupt so explosively that little material builds up near the vent. Eruption partly or entirely empty and underlying magma chambers which leave the region around the vent unsupported, causing it to sink or collapse under its weight. The surrounding basin-shaped depression is roughly circular and is usually several kilometers or more in diameter. The lava erupted from caldera volcanoes is very viscous and generally cooled at speeds with temperatures ranging from 650 var- degrees Celsius to 800 degrees Celsius. And this is called rhyolithic magma. Although caldera volcanoes are rare, they are most dangerous. Volcanic hazards from this type of eruption include widespread and ashfall, large paroxystic surges, and tsunami from caldera erupts. Example of caldera volcanoes in the Asia-Pacific region includes Rabaul volcanoes in Papua New Guinea and Krakatau volcano in Indonesia. Volcanic hazard. Volcanic hazards include explosion, lava flow, bombs or ballistics, ash or tephra, flows, pyroclastic surges, mud flows or lahars, landslides, earthquakes, ground deformation, tsunami, air shock, lightning, poisonous gas, and glacial outbursts, flooding known as geolautus. Each hard has a different consequence, although not all occurs in the eruption or associated with all volcanoes. Volcanic eruptions are measured using a simple descriptive index known as the volcanic index, which ranges from 0 to 8. The index combines the amount of material ejected with the height of eruption column and duration of the eruption. Volcanic activity frequently occurs at the boundaries of the earth style. The moving of these plates plays a significant role in the type of volcanoes formed, which influence its shape. Spreading plate margins, area of the earth where plates move away from each other, are called spreading or divided plate margins. In this area, volcanoes erupt are usually gentle explosion of ballistic lava. Most of these eruptions occur underwater where magma rises from the great depths below to fill the space created by the seafloor spreading. This occurs at the rate of 10 centimeters a year. Subducting plane margin. At subducting plane margin, one plate is pushed under a neighboring plate as they squeeze together. In this margin, wet sediment and seawater is forced down in addition to old weathering plate, and the addition of sediment, seawater, grates, and the cyclic lava and violent eruption contains ash. These volcanoes form classic cone shapes. Hotspot volcanoes. Locations of anomalous are commonly referred to as hotspot volcanoes. There are two currently debated explanations of how this volcano is generated. From hot mantle upwelling or plumes with rise at the great depths, hence not the term spot. The passive rising of melt or shadow depth that is not actually anomalously hot. Example include Hawaii Island and Yellowstone. If the plate over the plume move away the hot spot, a new volcanoes can be formed. The previous volcano pulls to become dormant and is actually extinct. This sequence from a volcanic chain just as Hawaii Islands because sometimes volcanoes can be two types. Islands the example of a volcano that falls into categories. It is a spreading plate margin volcanoes as well as hotspot volcanoes.